All right, welcome everybody to Wednesday of week 3. Today we're going to be talking about some pretty important topics. We're going to be talking about pointers today. Pointers are one of the all-time hardest topics in computer science. A lot of people have done programming for years and still don't understand pointers. Hopefully today's lesson will clarify them. A part of the reason why people have trouble with pointers is they don't understand why you would use them, right? And so what we're going to do today is justify using pointers. In fact, when I was working on SDF2 myself, I was like, oh, there's a great use for pointers here. And if you guys implement the thing that I'm going to show you today, I am offering you 20%, 2 bonus points on your homework assignment, whether or not you pass the test cases, if you do it correctly, if you do it with pointers. So let that motivate you, give you some extrinsic motivation for learning pointers. And it's also actually a really great case example of where pointers would actually be used, like where I would actually use them. A lot of times professors have to come up with these sort of contrived examples, right? Like we could like the classic contrived example of a pointer is you have like an integer x whose value is 42 and create an integer pointer that's pointing at it. So this says pointer is pointing at x. And so now we've got 2 different ways we can access x, which is confusing and stupid, and so we don't usually do that. Or is that image that I found earlier? Is it under memes? Yeah, there it is. Right, so you got an int pointer, and it's pointing at an integer, right? So you got Putter over here as Art Dwyer, who's kind of this guy who runs the San Francisco C++ group. He calls him a putter. So I call it putter ironically. So you've got a integer pointer here, and it's pointing at an integer. So we can call it putter, or we can call it Bob. Either way, we've got 2 different ways of talking about x. And if we wanted to change the value of x to 420, we could say x equals 420. Or we could say star Bob equals 420. These 2 lines of code, option 1, option 2, do exactly the same thing. What is a pointer? Okay, so a pointer holds an address in RAM, in memory, where another variable lives. And we typically, you should be able to point to a pointer. You should be able to point to a pointer. No. It holds an address in memory. And that sounds complicated. And so basically, you've got Bob here pointing at x. And if you want to access x, you do star Bob. Star Bob and x are literally exactly the same thing. This is called aliasing. You've got 2 different variables now that point at the same thing. You've got x, you've got Bob pointing at x. You don't write code this way. This way is completely contrived, right? This is done completely to just show you how pointers work, but it doesn't motivate you because you wouldn't write code like this, okay? So a better way of doing this would be like with a dynamic array, right? So you got an int pointer array equals new integer 100. And so this is going to make 100 integers all at once. Dynamic array makes 100 integers all at once. And of course, we have to delete it when we're done. Delete the array when we're done because of the rule of the Sith. For every new, there is a delete. For every master, there is an apprentice, right? And so this will temporarily until the delete comes in, make 100 ints. But that's still contrived. And the reason why it's contrived is because you just use a vector. Vectors, I mean, if you were going to make a vector, that's how you do it. They use new. But in modern C++, you still don't really use a pointer very often because you just use a vector instead and it would do it for you. And it's safer too. Because like, what if we just made just one integer, right? The type here, by the way, is identical, right? Except you can't use the delete with square brackets. You have to use regular delete. But it's still an int pointer. This is one of those issues with integer pointers, or any pointer in reality, is that you actually can't tell if they point at one thing or a lot of things. It's a problem. It's a problem in the language. It only has the beginning of a block of memory. It doesn't have the end included in it. So this is like kind of gnarly, and we can do this, and we can see out instead of R, we'll call this, I don't know, Sydney, and we'll see out Sydney, and then delete Sydney when we're done. So everybody, what value is going to be printed to the screen here? So Sydney is pointing at an integer. Now this is less contrived. Why? Because the integer that it's pointing at doesn't have a name. The only way we can print that value in RAM is through Sydney. There is no X anymore. There is no name for the variable. It's an anonymous block of memory somewhere within RAM, and we've got the memory address. That's all we have. So yeah, it's going to print 42 out. It's going to initialize a chunk of memory inside of the heap somewhere. Here's our map of memory. The stack's up at top of RAM. The heap grows upwards. The stack grows downwards. All regular variables you make, like if you make like integer x, y, z, all of these are stack allocated variables. Okay, so all of them are going to appear here, okay, within the stack. And the nice thing about the stack is every time you call a function, the function knows how many variables are within it. And there's what's called the stack pointer right here. It moves downwards, as you can see in the direction of the arrow here. Stack pointer moves down enough room so that x, y, and z now exist. When the function returns, the stack pointer goes back up. Those variables are deallocated. You don't have to worry about newing anything. You don't have to worry about deleting anything. They're called automatic variables back in the day. Auto keyword originally used to mean make it an automatic variable, but we never used it because all variables are auto by default. And so they repurposed the auto keyword. When you new something, though, it's going to appear down here in the heap. So when we new Sydney here, Sydney is pointing to some chunk of memory within the heap. And that memory is permanently allocated until we do a delete on it. And then it is released back to the operating system. There's other chunks of memory. There is the BSS, the read-only data, the data segment, things like that. Globals exist down here in the BSS. These don't really matter as much. Your code segment is here, but there's actually an important chunk of the whole equation missing here, and that is what I call the minefield of doom. So I'm going to have to add that to that graphic that I just blatantly copied from the internet. So if I come up here and make a new page and call this one 125.3, paste. There we go. So we can just scroll down maybe. So here is memory, and the top of memory is memory address 7ff f. So if you ever print out a pointer and you get a number that's like 7ff, that means that it's a stack allocated variable. So if we like see out the address of x and the address of y and the address of z, you'll see that all these guys are at address 7ff something something something, 7ff something something something, 7ff something something something, and this guy is 4 bytes away from that guy and 4 bytes away from that guy. So they're all 4 bytes away from each other because integers are 4 bytes on our system. Anytime you have a heap allocated thing, this is going to be like somewhere in the middle of RAM. So if we were to see out Sydney just by herself like that, that's going to be Sydney's memory address, and it's at 5, which is somewhere in the middle. Star Sydney means give me the value at Sydney. That's what the star operator means. So the reference operator means give me the address of a variable. So if you were to see out, if you were to see out the address of x, then that prints the memory address, the location in RAM where x is. We normally don't care too much about it, but we use that to get a pointer to something because it returns a pointer. And that says the star operator says give me the variable at that address. So the star and the reference operator, the reference and dereference operators are opposites to each other. So if you're to do something gnarly like, I don't know, something like this, like you could probably have them all, cancel out and just get some nice job security because nobody would understand your code. Learning is occurring. I always got confused with star and ampersand. Yeah, so the ampersand gives you a pointer to a variable. So if you say, int pointer Bob is equal to the address of X, now Bob is pointing at X. This returns a pointer to X. And then you can access X through Bob if you wanted to. And then when you see out star Bob, then let's make this, let's initialize this value here. This is going to print 10 because Bob is pointing at X. So we do star Bob that says, give me the variable at my address that I contain, and it gives you X. And so it's going to print 10 to the screen. Okay, so put these guys back, who cares? So when you've got this thing here, like when you call a new function, you've got this thing called a stack pointer, and the stack pointer moves downwards. So if you are calling a function, the function has X, Y, and Z. Then the stack pointer moves down. X, Y, and Z live until the function returns. When the function returns, the stack pointer moves back up, and thus they are automatically purged from existence, and the stack pointer is back up where it was before. So the ampersand is like the key, and the star is like the value. If memory was the dictionary, yes. If you want to think of RAM as a dictionary where the memory address is an integer, yeah, that makes sense. Okay. Now, benefits of using the heap, because you're like, why would you use the heap? Like, it's just extra work, right? Well, there's two things. One, things on the heap are permanent. So they are all managed by the programmer. You can allocate, like if you have a function call that loads a map, you don't want it going away when the function returns, right? That's bad, right? You call load map, and then when the function returns, the map vanishes. Can't do that. So anything you want to have persistent, anything that is going to be persistent, it's going to stick around for a while, you want that on the heap. And anything that is large, you want on the heap as well. Okay. The stack here is about 100 megabytes on our system. It's not a lot of RAM. It's enough for, like, if you want to make integer X, int X and Y and Z, sure, whatever. You're not going to run out of 100 megs doing that. 100 megs is plenty if you're just making, 32 bits at a time, whatever, But how much video do you think you can hold in 100 megabytes, right? Like, could you store a YouTube video in 100 megs, do you think? 10 seconds? Yeah. It's probably, you probably do like a TikTok, thing or something like that. You really don't want to fill up your stack with like video data because it's going to stack overflow and crash your program. Maybe a Vine or something like that. I don't know. So, so anything that's big, you have to use the heap for. And what you're probably used to doing, though, is just using a vector for it, because vectors allocate off the heap. But in this class, you're going to make a vector yourself. So you're going to get to do the allocations and deallocations yourself, but not for this assignment. For this assignment, we're doing something a little different. So is there a way to set the dedicated heap size to a larger amount of RAM? The stack size or the heap size? The heap's big, I think. I think on our system, I think I have the heap set to 2 gigs. 2 gigabytes here, okay? The stack, though, is small, okay? And it's deliberately small, actually. This is actually probably bigger than I want it for, like, legitimately. Like, when you have, like, an infinite loop and you're recursing infinitely, it only crashes once it runs out of stack space. So smaller stack space means that it crashes faster, which is a good thing, right? But yeah, this is actually configurable. If you go on the server and you type limits, limit, you can set stack size is supposedly set to 8 megs. So there you go. In practice, though, it will not crash until you hit about 100 megs. Okay, but that's a configurable parameter. You can adjust that however you want. core dump size is limited, is turned off basically. Data size, that's your heap, is unlimited. So effectively you can do all of RAM on the server. We got like 4 gigs on the server, but I think it only goes up to about 2 the last time I tested it. So, and yeah, I could quota you guys and things like that, but in general, my students have been pretty responsible with the server, and the only people that have accidentally done stuff has done so accidentally, not intentionally. Okay, so that's the stack, that's the heap, and if you want to work with the heap, you got to use pointers. All right, so there's motivation number 1. Okay, motivation for pointers. That's our lesson for today. Motivation for pointers. Number 1, heap stuff is all pointer based, and the heap's pretty useful. Okay. Now, it is a pain in the butt though. So here's wrong. We've got Sydney here. Let's get rid of all this stuff. We got Sydney here, and we do something like cn into the value pointed to by Cindy. After a while, you just sort of get used to using the pointer like just it's a regular variable, right? We're going to read into the value pointed to by Sydney. We're going to print out the value pointed to by Sydney. Star Sydney is just everywhere. It's just normal, right? So we'd say if star Sydney is less than, I don't know, 10, return, die or something like that. I don't know. Return 1, I don't know. 0. So make sure the value is positive. Die. Cool. Now, everything look good to you guys? We got a new, we got a delete, we're reading in values, we're writing out values, we're vetting them. This look pretty good to you guys, or do we have any problems with this code? What do you guys think? I'll take a moment to drink some delicious cup of joy coffee. Iced hallelujah. Pretty good. It doesn't matter if you die without deleting. Kind of does, right? Because it means we're memory leaking, right? So it's not huge because we're memory leaking right before we die, so maybe we don't care about it. But this brings up a bigger question, which is you can have a function, and the function can do things, and there could be multiple ways out from the function, right? You can have if statements and else statements, and what do we need to put here for this code to be correct on this line? What's the point of delete? It frees the memory up. So if you do a new and you don't do a delete, that memory is gone. You can't use it again. And if you have a function like this, and let's say int pointer r equals new int 1,000,000 integers, and we'll come back to Sydney in a second. For int I equals 0, I is less than 2000, I plus plus, foo. So it's going to call foo 2000 times, right? Every time we call foo, it allocates 4 megs of memory. Does it free it? No. So that memory is gone. So let's make it even more appalling. Let's make it like 100 million. So it's going to allocate 400 megs of RAM every time it calls foo. And then we'll call foo, and then we will sleep for 1 second. So every second it's allocating 400 megs of RAM. Run in the background, and we can see here. Let's see here. Is it running? Let's let's see here. Foo. Oh, I might have the optimizer on. Okay. G++. .cc. Let's do this. Allocates 400 megs, 400 megs, 400 megs. That memory is not coming back. So this is a problem, right? Every time we do this, we're newing memory, we're not deleting it. And so our memory usage is going to grow and grow and grow. And eventually we'll run out of RAM and it'll crash, right? So that's why you need to have a delete. Every new needs a delete. This frees 400 megs of RAM. This will alloc 400 megs of RAM. Okay. Killing the program does actually delete the memory. So when the operating system kills a program, it knows exactly how much memory has been allocated to that program and it recovers all of it. But the only way you can get that memory back is by killing the program. So that's something called a memory leak, and it's considered bad. So the longer your program's open, the more memory it uses. And the memory usage will just keep exceedingly growing over and over again. So that is a memory leak. And memory leaks are bad. That's why you want to have a delete. Now, the problem here is, like Alessandra said, we're going to be returning without deleting Sydney. So we're going to need to put a delete Sydney into here as well, right? So every branch, every way you can come out of a function has to have a delete for every new that's above it. And that gets complicated and that gets annoying. Like if you've got, like a bunch of different variables that are all nude, all of those are going to have to be deleted on every branch that goes through the program, no matter what. It's just awe. You just don't want to deal with it. Okay. So there is a better way. Okay. And so this code here, let me show you what it's going to look like. So G++ with no optimizer. The optimizer will delete a lot of this code. Sanitize equals address. .cc. Run it. It's going to read in 100. Everything worked fine. Type in -10. Memory leak. So in some branches of the code, it will work fine. It'll get to the delete and free up the memory. In some branches, when Sydney is less than 0, it will return without deleting the memory and it will leak memory. And so address sanitizer, this is something that you should take with you when you guys transfer to another institution. Address sanitizer is amazing. It's only about 7 years old at this point, and it is something that very few people know about for some reason. I'm not sure why. I spread the gospel of address sanitizer everywhere I go, but like just nobody's heard of it apparently. Address sanitizer will tell you when you screwed up memory, right? So it's going to tell you, in fact, right here, that you need debugging turned on. So whenever you're doing anything development-wise, you should have debugging turned on like that. The -G enables debugging. And then when you run it, everything's fine. You run it with a negative number, memory leak, main.cc, line 20. Okay? Main.cc, line 20. We have a new that did not have a delete. And the reason why we didn't have a delete was because we left early. So this presents basically an unsolvable problem. Like the last 50 years have taught us that humans are just not smart enough to actually do this properly. And so there is a better kind of pointer. I mean, raw pointers, this is something called a raw pointer. They're fine for some uses. But there's a better way of doing it. Oh, before I talk about those things, the delete, every time you do anything involving news and deletes, you should be running it with address sanitizer. It's enabled by default for you guys. So like if I were to become, I don't know, Increlli alias G++, you can see that I have ubsan and address sanitizer turned on for all of you secretly. So it's been on all along. The thing is, though, if you go to another college, they've never heard of it. So apparently, I don't know. I'm not sure why. But I'm trying to spread the word. Anyhow, take this with you. It will help you on your way. It's like this meme. If you guys are familiar with that one from the original Zelda. So address sanitizer you should take with you when you transfer to a different institution. Okay. All right. When you compile your code, you need to compile with -G, which is on by default for you guys as well. So let me show you some cool things. Let's set Sydney equal to 100. And it doesn't like that, so we're going to cast that to a memory address. So what is at memory address 100? You're looking at the map over here. You would think, okay, 0 maybe is around this instruction thing here. This is our code segment, it's sometimes called. No, there's actually something below it. And that's why I said I wanted to draw something in. So memory address 0, I call the minefield of doom. The technical term is the 0 page, but I like minefield of doom better. Anytime you read or write to anything around 0, the operating system will kill your program. Okay? That page of memory is marked as inaccessible. So if you try doing this, where you set Sydney to be pointing at memory address 100, which is inside of the minefield of doom, then it will kill your program for you. And you will get the infamous seg fault. Yep. So we try writing into Sydney, crash. Okay, we're getting a segmentation violation error. Okay, now if you don't have address sanitizer on, you will get the even more mysterious seg fault. So right here, segmentation fault core dumped with no explanation. What does that mean? Each one of these things here are called segments. Okay, and you violated these segments. You stepped on the minefield and exploded. So you got a segmentation violation, a seg fault. Okay, a seg fault, it's like in tennis. You know, you step over the line, you fault. This is a segmentation fault. You stepped over the line. So if you want to debug this kind of stuff, there is a tool written by my boy Richard Stallman, GDB a.out, called GDB, and you run the program, and then it's going to run your program inside of GDB. And so you can do whatever, you type some stuff in, and then when it crashes, it will actually tell you you crashed on the double right arrow operator. And if we backtrace, you can see it's crashing inside of the double right arrow operator that was called from main.cc line 22. So if we go up a stack frame, it'll tell you this is the line you crashed on. Boom. Okay. If you do address sanitizer, you don't even need to run the debugger. The debugger is often nice because with the debugger, you can actually do things like print the value of Sydney and things like that. Let's go back and do that one second. So you can do things like print the value of Sydney, and it's going to tell you the value of Sydney is 64, which is 100 in decimal, 64 in hex. And so if you ever look at a pointer, it's going to tell you this thing is an int pointer, and the value of it is 64. If you ever see a pointer pointing at any numbers near 0, you done goofed Ron, okay? Like, you screwed up bad, right? Anytime a pointer is pointing down here, you made a tragic and horrible and lethal mistake, okay? You have screwed up. So the debugger is useful for like doing things like that, like printing the value of a pointer and being like, The address sanitizer is better at just quickly locating where you died. Okay. So address sanitizer tells you segmentation violation, main.cc line 22. You don't have to fire up a debugger. You don't have to do anything. Hint, you are pointing at the 0 page. The 0 page. You tried writing to memory address 64 and screwed up. So that's your problem line right there. Main.cc, line 22. And it'll tell you that's where you screwed up. But that's really not what the bug is. The bug is actually here, right? So it'll tell you where the code died, but it doesn't tell you where the bad memory address came from. Okay. Now, there's a better way. There is a better way than this whole thing. Do you guys see what the problem is here? Like, we can have if statements, we can have else statements, like, you know, else if Sydney herself is less than, you know, memory address 200, return 1. Do you guys see what the problem is here? There's all these different routes through the code. And it's really hard to guarantee that this new is going to get matched to the delete. Right? Do you guys see the problem here? Like, this is a challenging problem. There's a better way. I need to delete inside the if and the else if. Yeah. You would have to have a delete Sydney here and here. Every single way you can get out of your code is going to have a delete for every single thing that you need above it. And so the Linux kernel actually solves this by doing a goto statement. Like, they'll actually have like a cleanup flag down there, and then they do like they do something absolutely horrible like this. So, so this is actually the C way of doing this kind of stuff. So each of the different branches never return. You only have one return ever at the very bottom, and all the cleanup stuff is right above the return. And all these things just go to the cleanup section, and they jump to it, which is garbage. You should not use gotos. But this is in the Linux kernel, so clearly they know what they're doing. Okay? So there's a better way. There's a better way. Okay? And the better way is using smart pointers. Okay, so if we want to have a pointer to something, we can do this. Unique pointer, or putter, as Arthur Dwyer calls it. We're going to make a unique pointer to an integer called putter, and it's going to be equal to make unique 42. And we're going to change the value it points to 420, and we'll see out the value that it points to. So what value is this going to print to the screen? This involves include memory. Okay. Make unique integer. Can't deduce the type, I guess. Okay. So, what value is going to get printed on this line right here? A unique pointer is basically just like a raw pointer, your basic pointer. But there's one really cool thing about it, which I'll explain in a second after you guys tell me what value it's going to print out. What do you guys think? 420. Good. We could also cn in the value, cn into putter, like that. Enter a value. $1,000, prints out 1,000. So again, you just kind of have to get comfortable with using stars like that. It's just a regular variable. It's just the pointer holds the memory address of the variable, so you access the variable just by using the star operator. Again, the star operator just gives you the variable there. Now, this variable has no name, right? There's no actual name for that variable. The only way of accessing it is by doing a star pointer. So cn into star pointer, cout from star pointer, and that's just reading and writing to a regular variable. Now, there's something very cool. This is heap allocated, right? So I could do this to make, a gig of RAM all at once or something, right? I'm making one int, but whatever. Same principle. How do I delete this? can't. And the reason why I can't delete it is because I didn't do it. And a unique pointer will delete itself. Yeah. So if we do something like this, like if the value pointed to by putter is less than 0, die. Whichever way, any way we can that comes out of main, it will automatically free up its memory for us automatically. There is zero chance we can screw this up. We also don't need to clutter our code with all these delete statements everywhere. We don't need to have a go-to, which, my lord, what decade is this? Whenever the pointer here goes out of scope, normally it's by just hitting the bottom of a function, but you could also die or you could return or something. If the value pointed to by pointer is bigger than 100, return 1. It does not matter. It automatically frees up its memory. No memory leak. We are good to go. So if we run the code again and type in 1,000, works fine. If we type in -100, it says bad input. There's no memory leak. Okay. Just to verify this, I'm going to compile it with address sanitizer on. And you can see no matter what value I pass in, there's no memory leak. Unique pointers are neat. Okay. They are super cool and neat. And there is another type of smart pointer called shared pointer. Now, the downside to a unique pointer, I don't know if it's a downside exactly. Well, I'll let you guess. Can I copy a unique pointer? If I've got a unique pointer, can I duplicate it? Well, it's unique, so maybe not. Alessandro says no, it wouldn't be unique. That is correct. You cannot, in fact, duplicate a unique pointer. And so this actually is oftentimes a problem because you want to pass it to a function or something. And pointers are usually passed by value, right? Pointers are actually primitives. They are just an integer really underneath the hood, an integer or a long, technically, that holds a memory address. And so pointers are passed by value. They're not usually passed by reference or anything. And so you can't actually pass a unique pointer by value because it would be duplicating it. So there is a second type of smart pointer called a smart pointer. And this smart pointer can be duplicated. That's the only difference, really. What do you not like about me? Make smart. Did I say smart? It's a smart pointer. It is a shared pointer. Sorry. They are called smart pointers, but the type is called shared pointer. Don't type and type it. Talk and type at the same time. Okay, and we can't call it pointer. We got to call it pointer 2. And there we go. So now we have a shared pointer. And so if we wanted to make a new shared pointer, auto pointer 3 equals pointer 2, we can duplicate it just fine. And so a lot of people use shared pointers for the convenience. A lot of times, you want to duplicate a pointer for whatever reason, you're going to traverse down a list and you just want to copy a pointer and run down the line. Shared pointers are honestly a little bit more convenient than unique pointers, but they have a little bit of a performance over it. Not a lot, a little bit of a performance overhead. They kind of keep track of how many times they've been duplicated. And once the number of duplications they have drops to 0, then it kills itself. So a unique pointer, it's very easy. When the unique pointer goes out of scope, it deletes the memory. Boom, there is 0 overhead basically for a unique pointer. A shared pointer, though, it has this little counter and it keeps track of how many copies, how many clones of itself it has. And once the number of clones is 0, then it goes away. It deallocates the memory. Smart. I know, right? It should have. We can fix this, Alessandro. We can fix this. All right, I'm going to be using smart putter as shared pointer. How about this? All right, it does not like that. We can fix this. We can fix this in post-production. It'll be fine. Yeah. How many students are going to have? No, it's backwards. Sorry. This is terrible. I'm not going to. Okay. There we go. All right. So. Yeah. How many of my students are going to turn in code like that? No, I should just not do that. Okay. It's very common actually to use auto here because the make shared function returns a shared pointer. Make unique returns a unique pointer. And so you actually don't need to write unique pointer angle bracket int. You don't need to write shared pointer angle bracket int. Anybody who's a professional programmer knows make shared creates a shared pointer. I just typed it out for you guys so that you would know what the type is, right? So you know that this is I almost typed it again. Shared pointer. Okay, I almost typed smart pointer again. But auto's nice, right? And so you guys all know how auto works. It deduces the type from the right-hand side. Like auto x equals 0. What type is x? It turns C++ into Python. I know, right? It's not. It doesn't have the dynamic binding of Python, but yeah, I think a lot of people grew up with Python because it's sort of the de facto intro language now, and they wanted that in C++. But really, the benefit for C++ is that sometimes these types get really long, and you just don't want to type it, and it's kind of redundant, right? Like the angle bracket int here is completely redundant with the angle bracket over there, right? Like, why type it twice, right? So, int, yes, int it is. What about that? 0 dot. What type is x now? It is in fact double. If you wanted it to be a float, you could do that. Now it's a float. What about hello world? It is an array of characters. Nope. This is why I don't like doing a lot of auto with students, because they think they know what the type of this is, and they're all wrong. All of you are wrong. This is not a string. It's not an array of characters. This is a pointer. This is a const char pointer. So it is a constant pointer, which means you cannot adjust the values through it. Like if I tried changing the lowercase e to a capital E, it doesn't work. It is a read-only pointer. It is a const char star. This is a string literal over here, a C-style string literal. All literals are constant, and it's a pointer to the beginning of memory. It's a pointer to the H. But it's a const pointer, so you can't change anything through it. So there you go. Not intuitive at all. And also the question in C, anyone know, this is 5 chars, right? Each char is 1 byte. How many bytes does this take up in memory? Hello, it's 5 letters. So how many bytes does that take up in memory? 4? Nope. You off by 1 the wrong way. This is actually 6 bytes long because it is an H, an E, an L, an L, an O, and a null terminator. So the absolute worst part of C and old school C++ are the strings. The strings are an absolute garbage mess to deal with. When I took 41, half the class was just learning to work with strings because it's so counterintuitive and people would always off by 1 in different ways. So if we have hello and we've got world, world is also 6 bytes, right? So how many bytes would it take if we strcatted them together, right? If we were to use strcat, which let's just make it C++, why not? What if we did this, x plus equals y? So this is now going to be hello world. How many bytes is that going to take up? So we had 6 bytes in the first one. We had 6 bytes in the second one. How many bytes is the concatenated hello world, no space in between, going to take up? 13? Wrong. 12? Wrong. 11? Yes. So tip 10, off by 1 the wrong way. And trust me, I've done it. Everybody who has done C strings has done it. We constantly go 1 the wrong way when trying to figure out the size of things, and it is absolute garbage. So one of the best things about modern C++ is that you don't have to worry about any of that anymore. There's just the string class, and it's nice. Okay, so now let's come to our second motivation for pointers. And the second motivation ties in with SDF2. And there is an obvious improvement to SDF2 that we can make that I will offer you 2 points of extra credit, 20% of your grade, if you do it. And we'll probably use a shared pointer for that. All right, so I don't want to retype all the classes, so I'm going to do something bad. Maybe copy recursive SDF2 to Bob's big boy, and seeding to Bob's big boy, and we're going to have vim main.cc. And here is your starter code. Okay. Does it help with invariance? No, but it's going to help with this. So this is something that might have annoyed some of you, right? So for this assignment, at every point in space, which is this block of code right here, for every row, for every column, in other words, for every point in space, you're going to say, hey, who is the closest asteroid to me? Who is the closest rectangle to me? Who is the closest circle to me? And this is okay. This is aight, right? This is vaguely acceptable, although it's kind of vaguely annoying at the same time that we have to have 3 different vectors, right? Imagine if we had 50 shapes. You know, we have pentagons and hexagons and nonagons and dodecahedrons, and you know what I mean? Like if we had like 20 different shapes, like forget about it. You know, like I don't want to make 20 vectors, and I mean this stupid thing down here would be like 20 different, you know what I mean? Like forget about it. I don't want to write that. So wouldn't it be nice? Here's the motivation. Wouldn't it be nice if instead of all this kind of stuff, we could just say, hey, give me a vector of shapes. Okay? Wouldn't that be cool? And we'll just call this back. Hang on a second. Holds not all the asteroids, hold all the shapes. Wouldn't that be cool? I think it'd be cool. Do you think it'd be cool? Having 1 vector instead of 3. All right. Yeah? Do you guys see the motivation? Right now we only have 3 shape. When there's 3 things, like that's oftentimes enough that I'm comfortable just typing it out, like X and Y and Z. Once I get more than 3 of something though, I'm just like, no, I don't like this anymore. 3 is kind of, you know, on the boundary. Okay, so asteroid, rectangular, circle. We're going to read a point in, and this will just be vector.pushback, and this will be vector.pushback, and this will be vector.pushback. Everything's going to be pushing back the same stuff. And down here, we only need 1 for loop, right? For every shape, we're going to find the closest person. Makes the code a lot cleaner, right? So we're going to do this by doing something called inheritance, okay? And we're going to have a full lecture on inheritance the week 14, I don't know, something like that. But when I was writing this assignment, I'm like, you know, this is actually kind of a good place to justify inheritance, okay? So what we'd like to do, right now we've got our like asteroid class, and we got our rectangle class, and we got our circle class, right? And because they're all different, they all have to go into different vectors. Vectors are all homogeneous. They all hold the same thing. Now, one approach we could take is we could use a variant. Variants allow you to store options of different things. But what we're going to do here is we're actually going to make a super class, because it's super. Wait, no, because it's going to be the parent class for all these people. And it's going to be called shape. And asteroids are going to inherit from it. And rectangles are going to inherit from it. And circles are going to inherit from it. And all shape is going to have on it is that it will say that every shape has a distance. I forgot the end. Distance to function on it. That's it. So if you are a shape, you have implemented the distance to function. And as you guys know, the asteroid class implements it, and the rectangle class implements it, and the circle class should implement it if you've done it. And so we can actually refactor our code fairly easily, but it's going to involve pointers, and people hate pointers, so that's why it's extra credit to motivate you to, overcome your personal inhibitions and dive into pointers. Okay, I thought inheritance was never the answer. In this case, it actually is, and actually, think about like Unreal Engine, right? Like imagine you want to have a vector holding all of the objects in your world. If you use inheritance, all of them can be in one vector instead of having like a different vector for doors and a different vector for rocks and a different vector for flowers. You can just have one vector holding all the objects in the world, and you just loop over it if you want to. So here is what we're going to do. So I'm going to make a thing called shape.h, and this is going to be a class called shape. And it's going to have absolutely no private member variables. And the reason for that, there's no such thing as a shape. There's only asteroids and rectangles and circles. There's no generic shape. So it doesn't have any, there's nothing to it. It's illusory, okay? And we're going to make something called a virtual function named distance2 that takes in a point. Let's just do the XY version of it. I don't want to worry about the alternate version for now. Distance2 taking in an X and a Y. And how do you compute the distance to a generic shape? How many sides does a shape have? Who knows? How far away is something from a shape that has no location or side? Like, it doesn't make any sense, right, to talk about a distance2 function. So what we do is we say there isn't one. We don't have a distance2 function. But your kids do. What was that line from Back to the Future? Each child of shape must implement this function. So what we're doing here is we're saying everybody who's a shape will have a distance2 function on it. That's it. Okay. So yeah, there is no default distance2 function. We could make one maybe sometimes for some inheritance, but I don't even, like, this could be a circle, it could be a point, it could be a convex hull, like, who knows? Like, there is no default distance2 function. So we're just saying all of our children will have one, but we don't. So you can't actually make a shape. Like, if you tried saying, like, make a shape, S, it won't work because there's, it's abstract. It's abstract. That's what that means. It doesn't actually have any implementation details. You can't actually make a shape. But you can make an asteroid and a rectangle and a circle, and those will be fine. I'll show you how to do that in a second. So there's a couple keywords up in here that are important. Virtual means our children will override this function. They will give their own implementation, right? The distance to a point is different from a distance to a circle, which is just different from the distance to a rectangle. And equals 0 means we have not implemented this function at all, so we cannot be made. You cannot make a shape because shapes are nebulous. They don't have any details. And that's it. That's all we have to do on this side. Now, on the other side, on point.h, we are going to do inheritance. So we are going to say point inherits from shape. And so this nonsense here, class shape means point inherits from shape, or point is a shape. And so in order to use this, we have to hashtag include shape.h. And expected class name, didn't I do this thing? Structure point inherits. Oh, not class. Sorry, public. Again, typing and talking at the same time is dangerous. Okay, so nope. Public shape. Okay, So that means that point inherits from shape. And I don't think we did this right. So there is another keyword, and this will be our last keyword, which is called override. And override ensures we are successfully overriding a parent function. And I don't think we are. I think I typed it in wrong. Yes. Okay. That's because this guy's const. Okay. That's where I screwed up. So if you want a child to override the parent, it must be exactly the same. Okay? If you have a const method and the parent isn't const, then it does not override it. So if we do this and come into here, do we need all this stuff? I don't think we do. We don't need you. We don't need you. We don't need you. Distance 2, we probably need. We'll probably need a 2-parameter constructor. Float new x, float new y. It's pretty common for the compiler-generated constructors to get turned off whenever you do anything vaguely complicated with a class. There we go. Actually, I didn't need to delete the other stuff. Oh, too late. So here we go. So we're done. So that's literally all the refactoring I had to do. I shouldn't have deleted all that stuff. All I really needed was the constructor here added. So let me go ahead and do it for rectangles so you guys can see the process again. Include point.h, and point.h includes shape.h, so I don't need to include shape.h. So step 1, add :public shape. Just like that. 2, we might have to add a constructor. Make sure distance 2 is override. That'll make sure that we're actually overriding it successfully. Const override. Because if you have a typo, like if you make it distance instead of distance, it's not overriding the parent. And so the override keyword here just makes sure that you are actually changing something in a parent class. So if you have any typos, like what I had before, I forgot the const before, then the override keyword will pick that up and be like, no, you screwed up. You don't have to have override, but it's very useful. So the parent has virtual. The parent has virtual here, and it is a virtual abstract function. And then the child is override, and then everything works nicely. It catches if there's any discrepancies between the two. And so the rectangle is overriding the distance 2 function of the parent. And we should probably implement this, huh? Return rand modulus 15. There we go. So the distance to a rectangle is now going to be some number from 0 to 14. There you go. Easy. It's not right, but it'll get us where we're going. All right. And then for the circle class, public shape. I'm just not even going to worry about circles. I'll leave that as an exercise to the reader. So we'll just pretend circles don't exist. There we go. Make it simple. All right. Now, the thing here is you can't just put a shape in here because shapes don't exist. You cannot make a vector of shapes because shapes are completely abstract. So here is the final motivation for pointers here. You have to use pointers. Anytime you do inheritance, you have to use pointers. So we are going to make a smirt pointer, which I'm not going to type as a smirt pointer. I'm going to call it a shared pointer to a shape. And we are going to push back. Remember, you need memory. And then when we do the pushback, we have to use which function. Which function makes a shared pointer? I don't remember. We've got a point, but a point is not a pointer, despite the name. What is the function that makes a shared pointer? And remember, it's got like an underscore in it. Make shared, very good. So we're going to do make shared out of asterisk. And same thing for the rectangle here. We're going to do make shared out of the rectangle. And now, leave the angle bracket on it, I guess. Actually, point class, rectangle class. Okay. And now our code is pretty good. The only difference here is we are going to be using arrow. That's it. Whenever you access things from a pointer, you use the arrow operator instead of the dot operator. In Java, everything's a dot operator. Pointers are basically, they just use dot. So now that we have a vector of smart pointers, instead of dot, we use arrow, hyphen, greater than, and we're done. So if we want to run this code, matching call, let's see what happened here. Unused parameter P, matching function call for the point. I think we might need to make some new this is probably not the issue, but check that. There we go. Everything worked fine. Okay, so we're going to have a 20 by 20 map. We're going to make an asteroid at 0, 0, an asteroid at 1919. We're done. There you go. There is an asteroid at 0, 0, an asteroid at 1919. Everything works fine. If we make a 20 by 20 with a rectangle in it that's at 10, 10 with a width of 5 and a height of 5, then you can see it floods the map with random data because I am not giving you the distance to function for a rectangle. Instead, it is just returning a random number for every point on the screen. But there you go. It works. And all you have to do is that, and that's 2 free extra credit points. So the kicker is that you make 1 vector instead of 3. And you see this highlighted comment that I have there. You might be wondering if there's a better way. Here it is. Here's the better way. So you make it a vector of shared pointer of shapes. And then down here, use pushback with make shared instead. And now, you see that? We only need 1 vector to hold all of the shapes instead of 3. So inside of main.csc, you change the vector of points or whatever to a vector of shared pointers of shapes. And then when you insert things, you have to use make shared to turn it into a shared pointer. You only need one for loop instead of 3. You make a, this is called an interface, or a pure virtual class. And so what this is saying is that everybody who's a shape, point, asterisk, rectangle, circle, anybody who's a shape will have a distance to function on them. And then when you write your rectangle class, you make sure you add this, public shape. So I am a member of the shape family. And so you just have to make sure I have a distance to function on me. And then everything just works beautifully. Okay. Any questions about this? I got a meeting I got to, but this, like I said, we're going to have more on inheritance. Like this is sort of the brief introduction to inheritance, but it'll make your code look a lot cleaner. And there's no risk of memory leaks because shared pointers can't leak memory. They're fine. They're A-OK. You can probably even do this with a unique. Yeah, works fine with unique pointers. Okay, so you guys got till Friday to get SDF2 done. Whether or not you should detour into Inheritanceville depends on you when you want to do that. It is 2 free points, so you can replay this video anytime you want and look at the different steps involved. I didn't do circle, but I'm not doing circle for anything for you guys, right? Like, I guess I did part of circle. I did that part, right? But you have to do all of circle. I'm leaving that up to you. So add the distance to function with the override tag on it. Technically, this code will still work if you don't have override. Override is just a safety measure, right? If you don't have it, the code will still run exactly the same way. It just keeps you from making a mistake. Like if you forget something, then it's not overriding something, then it tells you. So. Okay, so hopefully that motivates. Motivation for pointers. Heap stuff and inheritance. Inheritance only works with pointers. And that's one of the reasons why people hate inheritance is because you have to use pointers. You have to use the arrow operator instead of the dot. It's very scary. All right, so that is it for today. Good luck on your homework. It'll be due on Friday. There's not going to be any extensions for that. Zybooks I did extend to Monday because there were issues with the bookstore getting the books, so to speak, out in time. But that's it. Good luck. Peace.